Hello everyone, my name is Shashi, and today I will be walking you through the distributed system incident post-mortem for the scenario B. My assigned role for this analysis is BGP Peering Engineer. Let's dive right into the incident. In June 2019, a massive portion of the internet abruptly went dark for about 2 hours. We are talking about major platforms like Discord, Shopify, and Amazon Web Services become completely inaccessible for millions of users globally. Cloudflare alone saw a drop of 15% in the global traffic. This wasn't a malicious cyber attack, it was a fundamental failure of distributed routing. Today, I'm going to explain how a tiny regional ISP accidentally hijacked global traffic and why the internet's peering defenses failed to stop it. Let's move on to the second slide. So, to understand what went wrong, let's look at the timeline. At T0, the triggering event occurred inside a small regional ISP in Pennsylvania called DQE Communication. They are using a BGP optimizer software to improve their internal routing. However, this optimizer took Cloudflare standard broad IP prefixes and chopped them into thousands of highly specific smaller routes. At T plus 15 minutes, the first sign of failure leaked out. DQ accidentally advertises these highly specific routes outward to their provider. Allegheny Technologies. Allegheny then blindly forwarded these routes up to the chain to Verizon. This brings us to the T plus 25 minutes, the cascading failure. Verizon is a major tier 1 transit provider. When they accepted these routes and propagated them globally, the incident escalated from a local glitch to a global outage because BGP mathematically prefers the most specific route. The internet suddenly believed that the fastest way to reach Cloudware was through DQ's tiny network. Traffic flooded in, creating a massive bottleneck and catastrophic packet loss. Finally, around T plus 2 hours, Verizon engineers manually intervened, filtered out the bad routes, and global traffic was restored. So let's move on to the third slide. Looking at our system architecture, you can visualize You can visualize the massive flow of global internet traffic suddenly being forced through a tiny straw. The immediate cause was a massive BGP route DQ originated invalid, overly specific routes for Cloudflare network, effectively sucking global traffic into highly congested bottleneck. However, as a BGP engineer, I must emphasize that DQ's mistake was only the immediate trigger. The contributing factor and the reason this became a catastrophic failure was Verizon lack of route strict route acceptance control. A tier 1 network accepted thousands of incoming prefix advertisement from a smaller peer without validating if that peer actually had authority to announce those IP spaces. The underlying design issue here is that PGP was built a decade ago on an implicit trust model. It assumes peers are telling the truth. A design cannot survive modern internet scale without explicit verification. So move on to the next slide. This brings us to the core distributed system principle violated here, global state synchronization and the BGP trust model. BGP is essentially a distributed algorithm designed to synchronize the routing state of the entire internet. It relies on autonomous systems sharing their network paths to a global consensus on the best way to route data. However, this incident exposed the server limits of that distributed consensus because the protocol strictly obeys the most specific route wins rule. A single node broadcasting false state updates forced the entire global system to coverage on a broken reality. It provided that decentralized state synchronization without strict cryptographic validation at the edges is inherently fragile and highly vulnerable to local configuration errors. So, we'll move on to the mitigation and redesigns. So, What should have been different? Let's break down to the mitigation from peering engineer perspective. First, detection. Real-time PGP monitoring should have immediately triggered alerts. A massive spike in specific prefix advertisement for a major CDN originating from an unexpected small autonomous system is a massive anomaly that trigger an immediate pager alert. Second, a prevention. This is the most critical architectural change. We must enforce strict RPKI, which stands for Resource Public Key Infrastructure, alongside root origin validation. As peering engineers, we must implement strict prefix filtering policies at the edge. If an incoming BGP announcement isn't cryptographically signed and verified, our broader routers must drop it immediately before it propagates into our routing tables. Third, recovery. We need automated safeguard design directly into our peering policies. For example, implementing maximum prefix limit. If a peer suddenly advertises routes exceeding a predefined safe threshold, the router should automatically tear down the BGP session to isolate until an engineer can review it. So move on to the next slide, the references and checklist. Before concluding, I have reviewed the activity process checklist and ensure all pre-submission, including my role confirmation, mitigation planning, are complete. My analysis today is supported by technical post-mortem published by Cloudflare and the Internet Society, alongside the IETF RFCs outlining BGP prefix origin validation. That concludes my post-mortem on the 2019 Cloudflare BGP route link. Thank you for your time.